All right, it's time to learn about carboxylic acids and their derivatives. So we already know what a carboxylic acid is, and we have seen some of the derivatives previously, but we didn't necessarily call them carboxylic acid derivatives, but now we will. Let me explain. First of all, carboxylic acids all have a carbonyl group. Carbonyl is C double bond O. Nothing special about it, nothing fancy. It's just a C double bond O. There could be a bunch of miscellaneous things connected to these two legs, but carbonyl compound is a C double bond O containing thing. All carbonyls react in similar ways because, in somewhat similar ways, because that carbon, that's the carbonyl carbon, is an sp2 carbon. sp2 means bond angle of 120, so it's trigonal planar. Trigonal planar tells me that it's going to give me certain kind of stereochemistry sometimes. Yep, you got it, stereochemistry, it's coming back. Well, these things that are carbonyls that are trigonal planar, in every single one of them, the carbon there is electrophilic. Why is that carbon electrophilic? Well, there's a dipole pointed toward the oxygen in all carbonyl compounds, making that carbon partially positive. That carbon partially positive means it's an electrophile. It's an electrophile that is ready to be attacked by a nucleophile. So these guys, all of these carbonyls, they end up getting attacked by nucleophiles. So Dr. Bruce, she has divided our two types of carbonyls into class 1 and class 2 derivatives because they react differently. Carboxylic acids and their derivatives, she calls class 1 derivatives. They mainly do substitution reactions. The reason they do substitutions is they have a leaving group, while aldehydes and ketones are class 2. They do not have a leaving group, so they mostly do addition reactions. Again, class 1, carboxylic acids and their derivatives, substitutions. Class 2, aldehydes and ketones, they do additions. Ready? Aldehydes and ketones, why do they do additions? Because they don't have a leaving group. So I robbed this figure from your textbook that says aldehydes and ketones, the group highlighted in yellow, not a good leaving group. So they do addition reactions. Oops. While carboxylic acids and their derivatives mainly do substitutions. So these aren't on your slide. You'll have to write all these down. You should write them down, and you should write them down in this order. The order is important, and we'll talk about that momentarily. We'll talk first about the functional group names of all of these guys. The functional group names, this one is first one, hopefully you recognize. That's the very first functional group you have to learn. It's a carboxylic acid. So carboxylic acid over here to the side, it's not part of this list. It's over to the side. We'll talk about why. Now let's go through the naming of functional groups on this list. The top one, if that X is a halogen, that's an acyl halide. It could be an acyl bromide, acyl chloride. We'll see acyl chloride more often than bromide, but we'll see both occasionally. The second one I think you have seen before. I know you have seen before. I hope you recognize. It's an anhydride, an acid anhydride, all the same. The next one we have not seen before. We'll skip it momentarily. But the fourth one, that's an ester. I hope you recognize that as an ester, and the next one as an amide. So then back to the one above an ester. It looks a heck of a lot like an ester, but it's not quite like an ester. It's got a sulfur instead of an oxygen. So we call that a thioester. Real similar to an ester, but a little bit different. It's a thioester. And finally, the bottom one is a nitrile. It looks like a cyanide, but cyanide is an ion, a CN minus only. But when it's connected to a carbon group, it's a nitrile. So these guys are the carboxylic acid derivatives with a carboxylic acid over to the side. I said they're written in a particular order for a particular reason. Why are they written in that order? Well, it's all because of this table here. This table has acid bromide and acid chloride first, and then it's got things in order with carboxylic acid here, even though we had it off to the side. So we said these class 1 derivatives mostly do what kind of reaction? Substitution, mostly do substitution reactions. So that carbon that's partially positive, if it got attacked by a nucleophile, this group is the leaving group that goes away after the nucleophile attacks. So it's Br minus that goes away. Again, this is a partially positive carbon, so if a nucleophile attacks that carbon, this chlorine is what gets substituted. This chloride, is your leaving group. And again, on down the line, it's this group that's your leaving group in all of these cases. I don't know if it's worth it to point those out, but I will point those out. A bromide is your leaving group. A chloride is your leaving group. It's all the groups that were pink in our previous slide. These groups are the leaving groups. Are they all good leaving groups? Well, that all depends a little bit. Let's investigate. The way this table has it set up, this bromide is a base. The conjugate acid of that base is HBr. Chloride is a base. The conjugate acid is HCl. NH2 minus is a base. The conjugate acid is NH3. So these are all organized in order of increasing basicity. How do I say that? These are the acids of those conjugate bases. This smallest pKa is the strongest acid. This biggest pKa is the weakest acid. So this acid is the weakest acid, therefore this base is the strongest base. We've said more than once in this class, the weaker the base, the stronger, the weaker the base, the better the leaving group. Weaker bases make better leaving groups. So we wrote these in order of increasing basicity. Strongest base to weakest base. I did that in a funny order. Strongest base to weakest base, but really top to bottom, weakest base to strongest base. So that means this derivative is the most reactive derivative because it houses the best leaving group. So these are written in order of reactivity. This top one is the most reactive carboxylic acid derivative that we will discuss. And this is the least reactive, except nitriles are down there too, but they're just an outlier. This is the least reactive carboxylic acid derivative we'll discuss. So then in the same table, we've got class 2 derivatives from Dr. Bruce. That's aldehydes and ketones. Why are they class 2? They don't have good leaving groups. Their leaving groups are terrible, horrible, no good, very bad. They don't do substitutions, they do eliminations. False. They don't do substitutions, they do addition reactions, mostly. Okay, so moving along to carboxylic acids specifically and some information about how to make carboxylic acids, but first we have to start with the boring, awful nomenclature stuff. When we get started talking about each of these derivatives, the first thing we'll talk about is naming of them. Naming of all the derivatives relies on being able to name carboxylic acids themselves. So there's a few common names you have to memorize. I know, it's awful. A few common names you have to memorize, and then IUPAC names that will hopefully be intuitive. Formic acid. Formic acid is the common name for a 1-carbon carboxylic acid. The IUPAC name for the same acid, methanoic acid. Acetic acid is the common name for a 2-carbon carboxylic acid. IUPAC name for the same thing, ethanoic acid. Propionic, I hope we're seeing a pattern. Propionic acid is the 3-carbon common name, propanoic, 3-carbon IUPAC. Butyric, 4-carbon common, butanoic, 4-carbon IUPAC. Valeric, 5-carbon common, pentanoic, 5-carbon IUPAC. Caproic, 6-carbon common, hexanoic, 6-carbon IUPAC. So those acids are 6 common acids, 6 acids that you need to know the common name of, and you need to know the IUPAC name of. Every other acid bigger than that, we will rely on only the IUPAC name. All right, so that first name up there that you can hopefully deduce what it really is benzoic acid. That's this guy. It's benzene with a carboxylic acid. Next to benzoic acid is phthalic acid. Yeah, PH-TH, phthalic acid. That's benzene with a carboxylic acid, but no, not one, two carboxylic acids. Ortho to each other. Hopefully that word ortho is familiar to you. Malonic acid and acetoacetic acid have a bunch of stars beside them. They are very important in reactions we will learn in chapter 18. So they're not super important right now. They're not super important right now, but while we're talking about carboxylic acids, we might as well talk about these guys. So malonic acid is a diacid, 3 carbons in total. Acetoacetic is a monoacid and a ketone. It's got 4 carbons in total. The only difference between these two guys is what's on one end. Acetoacetic has a CH3, malonic has an acid there instead. Okay, so then let's name that bottom molecule. It looks like this. So if we want to give this guy a common name and an IUPAC name, the common name, the root name for a 4-carbon carboxylic acid, right? 4-carbon carboxylic acid. The common name for a 4-carbon carboxylic acid is butyric acid. Butyric acid has something hanging off of it. This is not a 2-chloro. We have to use alphas and betas. Common nomenclature says, this is my carbonyl carbon. This is my carboxylic acid carbon. Next door to my carboxylic acid carbon is alpha, then beta, then gamma, etc. So this is alpha chloro butyric acid. That's the common name. The IUPAC name, similar. It's a 4-carbon carboxylic acid, so it's butanoic acid. And the good news about IUPAC is you do get to use numbers, and carbon number 1 is the carboxylic acid carbon. So 1,2-chloro. 2-chloro-butanoic acid. Got it. So we will continue on paper for a minute while we name the next molecule. It's just the very next slide. Rather than switching back and forth, I'm going to continue on paper because it's easier than trying to mark things up digitally. All right, here's the carboxylic acid that we want to name. This guy. If I first start by trying to count the longest chain could be 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Uh-oh. We've got 2 ways to count 9 carbons. Which one is the right way? This one. So that pathway that steers up is the official right way to count this, because IUPAC rules say that you want the most branches on your parent chain, because that leads you to the simplest name. So this is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a nonanoic acid. Nonanoic acid, and there's a butyl on carbon 5 and a methyl on carbon 7. So 5-butyl, because it's alphabetic, 5-butyl, 7-methyl, nonanoic acid. And you say, hooray, we're finished. And I say, burr, burr. Not yet. Because we have not named R's and S's. Around this carbon, that is an asymmetric carbon, is carbon number 5R or is carbon number 5S? I'll give you a second while you think about it. Carbon number 5 is S. And I bet some of you, if you took the time to think about it, say, what? Why? Yep, if you compare this carbon, and that carbon, they're all CH2, so they're equal priority. But then when you compare here, here, and there, this carbon is higher priority because you've got 2 carbons connected. So this is actually my high priority branch. This is carbon branch number 1 priority. This is number 2 because if you follow down the line, you get to the carboxylic acid. Number 3 and number 4 is the hydrogen out front. So 1 to 2 to 3 clockwise looks like R, but my lowest priority is in the front. So I flip it, it is S. 5S. Carbon number 7 is also an asymmetric carbon. So is it R? Is it S? S. Hopefully that one didn't take you quite as long to think about. 5S, 7S, 5-butyl, 7-methyl, nonanoic acid. All right, back to the PowerPoint. So these guys we have already named. This bottom guy we've already named, but there's proof positive if you couldn't read my handwriting. And this guy we also named, let's see if we got it right, 5S, 7S, 5-butyl, 7-methyl, nonanoic acid. Ding, 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 whoop, whoop. So that's how to name carboxylic acids. Naming carboxylic acid derivatives is very similar. You start out by naming it as if it were the carboxylic acid. I know you can't see this on the big screen, but it's not super essential that you see it. It's not very detailed. This guy, you name this carboxylic acid, which is benzoic acid, and you drop the ic acid and call it 8. So this is now benzoate once it's the salt form of this guy. But sodium is the cation that's coming along for the ride. So this is sodium benzoate. Naming carboxylic acid salts. Salt cation name comes first, and then name instead of ic acid, it's an 8. All right. Whew. Painful naming. Blech. So let's continue our journey on carboxylic acids specifically and talk about how to make carboxylic acids. How do you make carboxylic acids? Old reactions that we have learned are how to make carboxylic acids using ozonolysis. Ozonolysis with oxidative workup is what that guy is. Hopefully he's familiar looking to you. Take that alkene, chop it in half, and stick O's on either side. Take that alkene, chop it in half, and stick O's where you did your chop. Then ask yourself, after I chop this, is this thing an aldehyde? If the answer is yes, and this answer is yes, it's an aldehyde, it oxidizes one step further to become a carboxylic acid. In addition, this side is an aldehyde, so it oxidizes one step further to become a carboxylic acid. Hopefully you recognize this is a 1-carbon carboxylic acid, so this is formic acid. Remember, that's the common name of a 1-carbon carboxylic acid. Formic acid is that little guy. That's an old reaction. Hopefully you remember how to do that one. Here's one that stems off of an old reaction, but is officially a new reaction for us. It's the same thing, but with an alkyne. Alkyne. Oh, that's terrible bond angle. I get mad at y'all for doing that. Alkyne, exact same thing. You're going to chop it in half, just like an alkene. You've got 2 carbons over here. So you got 2 carbons over here. Stick an oxygen where you chopped it. You got 3 carbons on this side. Stick an oxygen where you chopped it. The only thing that's different between alkenes and alkenes, this only turned into a carboxylic acid because it started out as an alkene and you were doing oxidative workup. Remember, that step is important, oxidative workup. For an alkyne, you are always going to turn your chopped pieces into an alkyne, into a carboxylic acid. Both of those pieces turn into carboxylic acids when you chop an alkyne with ozonolysis. Yeah. Okay. There's our carboxylic acids that we drew, including formic acid. There's our aldehyde. Nope. Our alkyne being chopped into 2 carboxylic acids. This is hopefully a very familiar reaction to you. This is an aromatic side chain reaction when you do a strong oxidizing agent. You do vigorous oxidation. We called this the Pac-Man reaction when we talked about it previously. That methyl on the side chain of my aromatic ring gets chewed into a carboxylic acid. It's a radical initiated mechanism. We didn't have to know that. We don't have to know it then. We didn't have to know it then. We don't have to know it now. But it's an oxidation process on the side chain. Remember, chromium is another good oxidizing agent. So when you heat chromium, acidic chromium with this guy, it's going to chew off all those side chains and turn both of those side chains into carboxylic acids. Remember, the deal with this is you cannot oxidize a tertiary carbon on the side chain. If your side over there does not have a benzylic hydrogen, if it's got 3 carbons there, nope, you cannot oxidize that thing. Okay, when we talked about alcohols back in chapter 11, unit 1 of this semester, when we talked about alcohols, we said alcohols can be oxidized as well. So chromium stuff we use to oxidize alcohols. When you oxidize a primary alcohol, like that first example, you end up oxidizing it to an aldehyde. But chromium is a strong oxidizing agent. So a strong oxidizing agent cannot stop at an aldehyde. It goes further and oxidizes to a carboxylic acid. Do you remember what reagent we could use to stop it? Oxidizing a primary alcohol to an aldehyde and stop there? Hopefully, you say PCC, but I bet some of you didn't, but it's okay. I forgive you. Primary alcohols can be oxidized with strong oxidizing agents to become carboxylic acids. So just like an alcohol can do that, if you start with an aldehyde, chromium is going to oxidize an aldehyde just the same way. This top reaction is a tougher oxidation, and it can do that. So you bet it can oxidize an aldehyde to become a carboxylic acid. That's chromium stuff. Chromium stuff is the most frequently chosen oxidizing agent for oxidizing alcohols, but there are a few others that would work as well. This guy is the Tollens reagent. We don't have to know a lot of reagents by name, but the Tollens reagent is one that I will kind of refer to frequently by name because it's officially a qual test. What the heck is a qual test? Well, it shows you some sort of apparent change, color change, or bubbling, fizzing, some sort of qualitative observation can be made to verify that a reaction has happened. So in all the reactions we're talking about right now, we're trying to make carboxylic acids. So hopefully you can recognize that this aldehyde will turn into a carboxylic acid simply because that's the theme of what we're talking about. How it happens? Well, we don't know. You and I. We will not be required to know how this happens. We just need to know that it happens. Silver oxide and ammonia are added to an aldehyde to give you a carboxylic acid. The qual test part comes in with when you get metallic silver as a byproduct. I hope some of your teachers in high school made you run some reactions maybe around Christmas time. You made some Christmas ornaments. You turned glassware into silver colored glassware. I hope they did that. The way they did that was this Tollens test. You have some solution that has an aldehyde in it. You add silver oxide and ammonia and you get silvered, mirrored glassware like that. We did it when I was a kid. Well, when I was in high school, we did it and made Christmas ornaments. We silvered test tubes and hung them on our Christmas tree at home and our Christmas tree at school. It was great. You should try it. Check out a video. Organometallics. Hopefully you haven't forgotten everything you know about organometallics, because they are coming back. We will talk about them again and again throughout this carbonyl chemistry stuff. Hopefully you remember the way to make them is you start with a halogen containing compound, most often a Br, add a little solid magnesium, and that magnesium squeezes his way between the carbon and the bromine to make a Grignard reaction, a Grignard reagent. That Grignard reagent has essentially a carbon with a minus, so it's a super good nucleophile, a super strong base. So when you add that thing to CO2, dry ice, the lab that we were going to do the week that got canceled, Grignard, super strong base, attacks the COO of that carbonyl dry ice CO2, carbon dioxide. There we go. Grignard adds to the carbonyl, so you end up making a new bond between benzene carbon and carbon dioxide carbon. You swung those electrons down, so you get an O minus and a little MIGBR floating around in solution, maybe kind of associated here ionically. We don't really care. Then you do some acid workup to that reaction, add some dilute HCl, sulfuric something, dilute acid workup. You end up protonating that thing to get a carboxylic acid, benzoic acid specifically here, which is exactly what we would have made in the Grignard lab that we won't get to do, sadly.